Welcome to my course on renewable energies. We have, I hope at least, and that you would agree, we have another fun lecture today where we derive some fundamental things or some important things. In this case, it will be the amount of wind energy that can be created in the atmosphere. And we'll make very fundamental assumptions, so very basic assumptions, in order to get an upper limit for that. You see that getting upper limits of what is in principle possible is one of the main things in this course. You will see the same thing also then when we analyze wind turbines. There also the question will be, what is the maximum efficiency that one can get? And in this case, we consider the atmosphere as a heat engine. And the question is, how much of the solar radiation that we receive can be transferred into wind energy? Once again, deriving these fundamental limits is a good way to check one's understanding of the fundamental processes that are going on. Okay, where did we end last time and how does it connect to what we want to do today? We were looking at endo-reversible heat engines, the Curzon-Albon machine. So I mentioned that it was not really Curzon and Albon who discovered that machine, but that's frequently the case that others get credit for what a third party has actually invented or established. In this case, the difference was in writing a good paper and perhaps a not so widespread paper, not so good paper. Well, the Curzon-Albon machine. Let us review this a little bit. So I go back to the very beginning of the last chapter where we introduced this machine. So we said that we have internally a Carnot engine. So an engine for which the Carnot efficiency holds, namely 1 minus T2 divided by T1, right? And in this case, the role of T1 is taken by T3 and the role of T2 is taken by T4. So here no entropy is generated. However, this Carnot engine is coupled to the environment by two heat conductors, R1 and R2, as you see here. And in the heat conductors, once you understand what entropy means, it is clear, it is evident that entropy is generated in these heat conductors just because the temperature here is lower than it is here, and the entropy is Q divided by the absolute temperature. So you see that, of course, the same temperature goes in as goes out, and therefore we generate entropy here. Today, we want to discuss a different type of heat transfer between the environment and the upper temperature level of the Carnot engine. But the thing I want you to look at is how the heat that goes from T1 to T3, how this is connected or how this can be calculated. And for heat conduction, it was a formula similar to or mathematically identical to Ohm's law. And today we want to use another way of heat transfer, namely one that's relevant for the system that we want to look at, namely the sun driving winds in our atmosphere. And what we want to discuss there is what you can call the Stefan Bitzmann engine, also nobody, neither Stefan nor Boltzmann discussed this type of heat engine. It's just the reason that the Stefan-Boltzmann law governs this machine. I don't want to repeat all the steps that we did here. I rather want to just show these steps on a PowerPoint presentation, and this is the reason why I switched to this now. So this chapter here, so the Stefan-Boltzmann engine, this I have here on this presentation, but I just see that a window here clutters my screen. Sorry for that. So, again, we have here a Carnot machine inside, yeah, but different from what we had so far. This Carnot engine is coupled to the surrounding by radiation, not by heat conduction, but by radiation. And therefore, instead of the relations that we had so far, namely Fourier's law, or looks like Ohm's law, right? We now have these typical Stefan-Boltzmann law type things with the temperature to the fourth power, right? And we'll come to the explicit expressions in a minute, but you would know them pretty much already. Namely, this is the radiation that the sun emits, right, and that we receive on Earth. So basically, what we have to find here is something like the dilution factor, Stefan-Boltzmann constant, and the temperature of the sun to the fourth power. And then here, this is, well, what Earth re-radiates. Right? And actually there's a second part of that. So what we want to do is that we say, well, there's a hot side on the Earth and there is a cold side on the Earth, and in a very simplistic and actually, at least for Earth, basically wrong model, we would say, well, there's the day side and there's the night side, right? And therefore we would say that this here would be the day side, yeah? So the hemisphere on the day side, that radiates to space, and this here would be the night side also, yeah? Well, rather this one here. Okay, but for the time being, we just leave it like that, yeah? So we just take these as factors, and we try to work our way through this. And of course, well, this looks much more ugly than previously because we have now the temperature to the fourth power, and so this would lead to very nonlinear equations. And therefore, these equations are in general not so easy to solve, but there are special cases for which this is still possible, namely for the case where the temperature T2 is 0. And this is actually pretty much the case in our situation, because we consider that our heat engine re-radiates to space. So the planet re-radiates to space, and the temperature of space is 3K or so, right? And this is basically 0, in particular if you consider that you take it to the fourth power and compare that to all the other temperatures, at least 2 orders, well, approximately 2 orders of magnitude higher, or for the sun actually 3 orders of magnitude higher, and all of that taken to the fourth power. Yeah? So now, when we have this, then we can continue. Yeah? So if we insert this into conservation of entropy for the case that T2 is equal to 0, then we get this expression here, right? And this we can immediately solve for the temperature T4, so for this temperature here. and substitute it into the efficiency of the Carnot engine that's described here, right? So, and then a few lines of, so we just substitute T4 here, and then after a few lines, you get an expression for T3 to the fourth power. Of course, you can also take the fourth square root, the fourth root, and this results then in this equation 32, right? Now we can go on and substitute this into equation 30, so into this equation here, right? And then we get an expression for Q. And once we have an expression for Q, we can, using the efficiency, we can get an expression for the work. And in our case, the work will be the energy, so the kinetic energy in the wind, right? And in our case, then, for this Stefan Boltzmann machine, this leads to this expression 34. Just the same philosophy that we did for the Curson-Albon machine. Okay, well, then we can of course look at the characteristics for this for this Stefan Boltzmann machine, and what you find is that it looks pretty much the same way, or this qualitatively in the same way as for the Curson-Albon machine. It is just a little bit more edgy. It's not so round, right? You see this in particular if you look at the work as a function of efficiency, right? So this would actually be the wind energy, the kinetic energy in the wind, as a function of the efficiency of the heat engine, which is the atmosphere. Once again, we consider the atmosphere as a heat engine, and the air actually as the work fluid in this heat engine. Yeah. Okay, so if we solve this for T4, then we get an expression for then we get this expression, and then we can substitute all these equations, and we finally get this expression here for T4. Right? So you see that once we have the coupling constants G1 and G3, and we choose an efficiency, then we can get we can calculate these intermediate temperatures. Right? So the day side temperature, which would be T3, and the night side temperature, which would be T4 for our case. Right? And the environment, once again, one is the sun, right, and the other is deep space, so 3 kelvins. Okay. Yeah. Now we do this. Yeah. We calculate the work given all these expressions, and what we get is this kind. Well, this is actually. Yeah. We leave it by this here. Okay, so the next thing then would be to actually apply this to a system, this is then the next chapter. This is chapter 4, namely generation of wind energy in the atmosphere using the concepts that we established so far. Okay, well, so chapter 4, generation of wind energy in the atmosphere. And we start with what is called the Gordon-Samy model. So this relates to a paper by Gordon and Sami. They wrote a paper in 1989, again in the American Journal of Physics. And this paper has the title, Wind Energy as a Solar-Driven Heat Engine. So the title says exactly what I announced before. So the Gordon-Sami model. Okay, so the situation that we want to look at is the following. So we have Sun here, and our planet here. So Sun is here, and here is our planet. And what we assume is that it's not rotating very fast, right? So that we have a day side, a permanent day side more or less, and a permanent night side. And of course the day side is much warmer than the night side, and so so the atmosphere here mediates a heat engine such that the temperature difference here is such that there flows heat from the hot side to the cold side. Okay, we start by describing it a little bit. So we think about a hypothetical planet with a day side, with a day and a night hemisphere. Is considered. So the day side has temperature T3, and the night side temperature T4. And these temperatures are considered to be the upper and the lower temperature level of a Carnot engine. They are considered the upper and lower temperature level for a Carnot engine. For a Carnot engine, and this is actually the wind. Hypothetical planet. You figure, of course, that this is not very closely to the Earth, because the Earth is rotating so fast that the temperature difference between the day and night side is more or less negligible. What we have on our planet is rather that the polar region is much colder than the equatorial region, and therefore this heat engine is only a very rough approximation. But of course it's an extreme approximation, so it's an extreme case. So what we expect is that the temperature differences in this engine are much bigger than on Earth, and therefore also there will be more wind, so the efficiency of wind generation will be higher. than on Earth, so this gives an upper limit. So in this case, it makes, so it is along the philosophy that we actually want to follow. We assume, of course, equilibrium, otherwise we can't do thermodynamics. We assume equilibrium, meaning that as much heat as the Earth receives, it also, or this planet receives, it also has to re-radiate into space. We assume equilibrium, and this means absorbed energy must equal radiated energy. It's a little bit problematic, this assumption, because what we assume is actually that we convert some of the energy into work, right? And this work somehow doesn't appear in our budget any longer. Yeah? So this is there's a conflicting assumption here. We will later try to fix it. But for the time being, we could say we don't expect a lot of wind energy to be generated, and so this may at least be a reasonable assumption. Yeah? So there's a contradiction. There is an inherent contradiction in our model because we expect work to be generated which, however, we fail to include into our budget. We fail to include in the energy budget. Yeah? Well, but now let us write down a few formulas, namely on how much heat is transferred from the sun to Earth, and then from the day side of Earth to space, and from the night side of Earth to space. So, heat from sun to Earth and from Earth to space. And for the sun, it's a well-known equation. Q1 is just pi times r squared sigma 1 minus the albedo, then the dilution factor, and T1 to the fourth power, so the temperature of the sun to the fourth power. So remember my lecture on global warming. So there we established exactly this formula, and if you just listened it for entertainment, then I would like to ask you to look at it once again, because these are very important concepts. So this is the equation from sun to Earth. Sun to Earth. Well, I mean planet. Yeah, so when I say Earth, I don't really mean Earth. I mean some hypothetical planet as said above. And now from the day side to space, so what we said in this lecture, in this fourth lecture 2 weeks ago, we said that the Earth has a certain temperature and therefore it radiates like a black body. It has a temperature of around 300 Kelvin and therefore radiates in the far infrared to space. And of course, what we have to take into account is the entire surface of Earth, while for this equation, so for the first equation, we just take the projected area, which makes sense. Yeah? So we radiate over this entire area. Yeah? So this is what we describe here in Q3 and Q4. But the Earth receives, of course, only, on the projected area, or according to the projected area, radiation from Sun. Yeah? So what we have to write, therefore, is here 2 pi, because this is the day side, 2 pi times the radius of the Earth squared times sigma, and now the temperature of the day side to the 4th power. And I said we consider the Earth as a black body. Well, not quite. What we also take into account is the greenhouse effect, and now we model it as Earth that has a smaller emissivity than a black body, right? So we write here 1 minus gamma. And you might remember that in the lecture 2 weeks ago, we introduced a function, or we introduced beta. And this was the fraction of infrared radiation that was absorbed in the atmosphere. If you do the calculation, then you find that this gamma here, that this is equal to beta divided by 2, right? Okay, yeah, so in this model, or in this way of modeling things, we treat the Earth as a gray body, actually, with an emissivity that is a little bit smaller than 1. Well, it's quite a bit smaller than 1, so something like 60% or something, or so, right? So this is how we take into account the greenhouse effect. Actually, the correction due to the greenhouse effect is not so large. And the same thing for the night side, right? So we have 2 pi r squared times sigma times 1 over gamma times the temperature of the night side. Yeah, so this is day side to space, and this is the night side to space. Yeah. And now, if you compare this to the Stefan Bitzmann machine that we just discussed, then you can identify the coupling constants. Yeah? So compare to the Stefan Bitzmann machine, and then you find the coupling constants, namely G1 is equal to pi times r squared, yeah, so the radius of Earth, times sigma times 1 minus rho, 1 minus the albedo, times the dilution factor. And the same thing you can find for G3, which is actually equal to G4. And this is 2 pi times r squared times sigma times 1 minus gamma. Right? And just because we need it later, we calculate G1 divided by G3. And what you get is, of course, 1 minus rho times F divided by 2 times 1 minus gamma. and there you can plug in numbers that are typical for Earth. So 1 minus rho, this would be 1 minus 0.3, right? The albedo was approximately 30%, pretty exactly 30% actually. And the dilution factor is 2.16 times 10 to the minus 5. And then we have to divide by 2 and 1 minus gamma. This gamma was 0.39. And, well, if you do this, then you find 1.24 times 10 to the minus 5. Yeah, just for later use if we want to calculate really something. Well, now if we consider the work that we have calculated for the Stefan Bitzmann machine, then we can immediately calculate how much wind we generate per or in relation to the solar radiation that is received, right? And this we can define as the solar efficiency. Yeah, so how much wind, how much kinetic wind energy is created per received radiation. So considering equation 334. Yeah, so this was this equation that we derived. So just let us go a few slides back. Yeah, so this is this equation here. Yeah. And what we do is that we divide it through the radiation that we receive, and this turns out to be just this thing here. Right? So we get quite a simple formula. Quite remarkable, actually. So, considering this equation 334, these coupling factors is already sufficient to derive the efficiency of wind generation. Of wind energy generation. Yeah, so we define the solar efficiency. And yeah, so we have small w. This is the generated wind energy. Wind energy divided by the absorbed solar radiation. Yeah? And the absorbed solar radiation, this is what you find here in this equation. Well, I didn't give them numbers, yeah? So in these equations here, right? Okay, well, and what we find then is capital W. Yeah, so this is this equation 334 divided by G1 times T1 to the fourth power. Yeah. So let's give them numbers here. So actually this is supposed to be equation 1 and this here is supposed to be equation 2. So now if we use that G3 is equal to G4, then we can immediately give the result. So using G3 is equal to G4, we get that W is equal to eta times 1 minus eta to the third power divided by 1 plus 1 minus eta to the third power, right? And now we can do the same thing then as we did for the Curzon-Albon machine. Namely, we can plot this solar efficiency as a function of the efficiency of the Carnot engine, right? So don't mix that up. Yeah? So these two efficiencies. So we have the efficiency of the Carnot engine, and we have the well, we also call it efficiency. We have the efficiency of conversion of solar radiation, of absorbed solar radiation to kinetic energy of air, namely wind. So we now plot this thing here, and I prepared that. Yeah, so this looks like shown here. Right, so we have here the efficiency, and here we have this function here, and we find a nice maximum somewhere at, well, a little bit more than 0.3, I would say, and the efficiency is close to 8%, right? It's something like this. Yeah. Yeah, so in principle, it's possible to find the maximum analytically, but it's a little bit nasty. So let's just do it by numerically. So in principle, it is possible to find the maximum of W as a function of eta analytically. However, we just do it numerically. And the result is that the maximum is 7.6% at eta max roughly 0.3, right? But there's a remarkable fact about this result here, because you see that it doesn't depend on the dilution factor, right? And therefore it doesn't depend on the distance from Sun to Earth. It doesn't depend on the temperature of the Sun, right? So really a very general result. Okay. Well, so in principle, this holds as an upper maximum for all planets. And it is, of course, clear that there was one basic assumption that we put in, which is, of course, not realized in many planets, namely that we have this planet that obviously all the time has a fixed, which doesn't rotate relative to the Sun, so that, or at least rotates very slowly. So this is certainly an unusual situation here. Well, Venus actually rotates fairly slowly, and so one might try to apply this to Venus. Yeah? So let's do that. So we check out Venus. There we have that eta is equal to 0. So eta equal to 0.3 is of course in general valid. And then we get 1 minus eta equal to T4 over T3. T3 I wanted to write. So that would be 0.7. And then using Venus temperature, as what one measures, namely 733 Kelvin as day side, then this would lead to T3 equal to T4. Equal to 713 Kelvin. I have to check these numbers. This doesn't seem... I have to check this. Yeah? So, this is not nearly the case. And the reason is that the atmosphere is very dense on Venus, and so there is a strong mixing between the different areas that receive different amounts of sunshine. Yeah? So the winds on Venus are so strong that the temperature is very uniform, that the temperature is very uniform. So we should improve our model a little bit. And this is actually what we do in the next chapter. And this is called the De Vos-Vlater model. Again, this was a paper in the American Journal of Physics by these two people from 1991. Actually, I put both papers on the Moodle, so you can retrieve it and read these papers. So the presentation there is actually a little bit different from the one here. The presentation here follows more the book by De Vos. Let us continue with the De Vos-Vlater model. And I start with the headline, of course. So 4.2, the De Vos-Vlater model. And the following sketch here should explain how this differs from the one that we had before. So, yeah. And you also see that we fix one of the problems of the Gordon-Samy model. So in the Gordon-Samy model, the work that was produced went just out of the borders of consideration. And now we assume, or now we realize, that the work that's generated in the end will be transformed to heat again through friction in the atmosphere, friction with the ground, and so on and so forth. Right? So what we assume is that a fraction alpha of that work is converted into heat and goes to the upper level here. And another fraction, so the rest, 1 minus alpha of that work, goes to the lower temperature level. So this will be the De Vos-Vlader model. But before I start with that, let's make a brief break. I prepared here some tea for me, and I hope you also take a few minutes and get your also some tea. I should have switched it on before so that the tea would now be ready. So if you have any comments here to the lecture, any questions, you can of course write to in the chat, and I also would try to answer these questions. So water is boiling slowly or getting hot. No questions, no remarks? So actually 11 students are watching. This is what I get from the analytics, from YouTube analytics. So. Oops. And the rest apparently is watching the lecture later. Okay, so I have a cup of tea. Then we can continue slowly here. Well, just compare to what we had here. Yeah? So what we derived here was, or what we looked at, were these equations for the heat. Right, so that so we had Q1 here, and then here Q3 and Q4, and now we consider so we actually look at the situation closer to the in a more formal way. Yeah, so we go back to basically the Stefan Bitzmann machine, and perhaps I should write that. We should review that on the slides. And so we have here these two equations that we will change now, right? So we will modify these two equations basically. This is how we start. right? And of course, what we add here is the fraction of work that goes to the upper and to the lower level. So we add these fractions here to these equations. That's it basically, and then we continue in the same way as we did it before, and this will change our formulas a little bit. It's too hot. Okay, good. Let us do that. So, yeah, so this model improves the Gordon-Samy model by taking into account the kinetic energy or the work generated. In the energy budget. And you see how it is budget. Okay, so, and this means, this means that Q1 is equal now to G1 times T1 to the fourth power minus G3 to the fourth power, and now plus alpha times the work. And similarly, Q2 is equal to G3 times T4 to the fourth power, T4 to the fourth power, minus 1 minus alpha times the work. Yes. Okay, yeah, and of course G1 and G3, and they are given by the equations that we, by these equations, yeah, by these equations here. Okay, so now we have to solve that, and of course there are a few other things that we need. We need a few more equations to solve it, and those which are quite obvious is of course energy conservation, right? So Q2 plus W is equal to Q1. That's clear, energy conservation. But in addition, we have okay, so there is a remark here. I forgot here the index 3. Okay, so two other equations that we have, one for energy conservation and the other for entropy conservation. Remember, we said that this machine is a Carnot engine, and therefore we know that there is no entropy produced, or the entropy carried by Q1 is the same than the one carried by Q2. Okay, two additional equations. Two additional equations, namely energy conservation From this we get that Q1 is equal to Q2 plus W plus the work, and entropy conservation, which means that Q1 divided by T3 equals Q2 divided by T4, right? Or explicitly, the letter explicitly, then we would have G1 times T1 to the 4th power minus G3 T3 to the 4th power plus alpha times W divided by T3 is equal to G3 times T4 to the 4th power minus 1 minus alpha times W divided by T4. That's equation 12. And actually these here are equations 10 and 11. So next we need, of course, T3 and T4, and we obtain them from radiative equilibrium. So derive T3 and T4 from radiative equilibrium. And, well, we said this already for the Gordon-Samy model. G1 times T1 to the 4th power, so this is the radiation received, is equal to G3 times T3 to the 4th power, day side and night side, plus G3 T4 to the 4th power. Right, so nothing new in this respect. Yeah. So there you might ask yourself, aren't we repeating here the inconsistency of the Gordon-Samy model? No, we don't, because this is just radiative equilibrium. Yeah, so this must hold anyway. Yeah, so there's no inconsistency here. So then we solve this equation 13 for T4. So solve 13 for T4. And this results in T4 to the 4th power. Yeah, so actually I solve it for T4 to the 4th power. So we have G1 divided by G3, T1 to the 4th power minus T3 to the 4th power. Equation 14. Yeah, and this we substitute into the efficiency, into the Carnot efficiency. So substitution into eta equals 1 minus T4 over T3, right? And from this we get eta equals 1 minus 1 over T3, and then the 4th square root of G1 divided by G3, T1 to the 4th power, of course, minus T3 to the 4th power, and if we transfer T3 into the root, into the 4th root, then we get 1 minus 4th root G1 divided by G3, T1 to the 4th power divided by T3 to the 4th power minus 1. And this can further, this can further be rearranged such that this force root is equal to 1 minus eta, or taking the force power, we would get that this expression G1 divided by G3, T1 to the force power divided by T3 to the force power minus 1. So, yeah, so this thing here sits, of course, here, that this is equal to 1 minus eta to the force power. Yeah, so 1 minus eta to the force power. And then we can solve for T3. Yeah, so we can try to get to find the temperature T3. So we would have then G1 divided by G3. Remember that we calculated that already. For us, we even have a numerical value for that. Namely, these 1.24 times 10 to the minus 5. But here, yeah, so we bring this term 1, yeah, so we bring it to the other side. And then we have 1 plus 1 minus eta to the force power. And from this we get T3 to the force power is equal to G1 divided by G3, T1 to the force power. And then we have here 1 plus 1 minus eta to the force power. Right? Okay. Yeah, and now we can get. Now we can try to find. We can try to find here another expression for T4. So this is equation 15 here. So in order to compute T4, we plug 15 into 14. Yeah. And what we then get is T4 to the force power is equal to 1 minus eta to the force power divided by 1 plus 1 minus eta to the force power, G1 divided by G3, T1 to the force power. So that's equation 16. And now we can calculate the work. And yeah, so this is a lot of things to write. I don't want to do this, to do all of that. So what I would do is that I plug in equation 15 and 16 into this equation 12. Right? So what you see is that, so what you see, what we have here, so you always have to remember what is known and what is not known. Yeah, so known is, of course, the temperature of sun. We consider everything as a function of eta, yeah, so as usual, so this is also known. But of course, T4 and T3, this is per se not known. This is the temperature of the day and night side of the planet. And now we can eliminate these terms here, and then we would have something where we only have the work, but not all the these two other temperatures, T3 and T4, that we don't know. Yeah? And you see that actually in each of them there's only T1 and eta. Okay, so the next point would be to substitute 15 and 16 into 12. Right? And then there's a longer but trivial calculation. I don't want to do it here in full detail, but rather write the result. So what we get is eta 1 minus eta to the fourth power, then 1 minus alpha times eta, and then 1 plus 1 minus eta to the fourth power, times G1 times T1 to the fourth power. That's equation 17. Yeah? And from this equation you already see that we again can simply write the solar efficiency, this small w, by dividing through the solar energy that is received by Earth or by the planet, which is actually this thing here. Yeah, so just dividing through G1 times T1 to the fourth power will give us the solar efficiency. Yeah, so T1 times T1 to the fourth power is the absorbed solar radiation. So dividing, so making clear that I left out a few points here. Dividing by the absorbed radiation, which is G1 times T1 to the fourth power, results in the solar efficiency W. So, and this means we have W is equal to eta 1 minus eta to the fourth power, 1 minus alpha times eta, 1 plus 1 minus eta to the fourth power. That's it. Yeah? So that's equation 18. Yeah, and this we can again just plot. And what we could do is to just look at a few typical cases, namely actually the case where, say, all the work or the wind energy is somehow converted into heat on the day side, or we can look at the other extreme where all the wind energy is dissipated on the night side. Of course, none of these extreme cases is realistic. Rather, you would say, well, pretty much the same amount is dissipated on both sides. But we look at these extreme cases and then also at the case where the energy dissipation is equal. And I plotted that. And what I get are these three curves here, where you see here the red curve for alpha equals to 1. Then all the wind energy is transformed into heat on the day side. Here the opposite on the night side, and now here the intermediate situation. And this kind of makes sense. Why? Well, when all the heat, when all the wind energy is dissipated on the day side gets warmer than without this extension of the model, without this extension of the Sami-Gordon model. And therefore, the temperature difference gets larger between day side and night side. And this means that the efficiency of the Carnot engine increases, right? Conversely, if all the heat is dissipated on the night side, then the night side, the cold side, gets warmer and the temperature difference gets smaller. Well, and here we have the situation in between, right? Okay, well, yeah. Yeah, so limiting cases. Namely, the first one would be alpha is equal to 1. And what we then get is a maximum solar efficiency of 8.3%. Yeah? And a remark here, these 8.3% are different from the Gordon-Samy model. Right, because there the wind energy does ended up outside the budget. Yeah? So this is different from the Gordon-Samy model, but actually not very different. Right? The next thing would be, well, alpha equals to 0, right? Meaning all wind energy is dissipated on the night side. Heats the night side. And therefore, we expect a smaller solar efficiency, and we get a smaller efficiency. It is 6.0%, right? And then the intermediate case, equal shares go to the day and night side. There we get a maximum solar efficiency of 6.9%. Yeah? One remark concerning why we are interested in the maximum of the solar efficiency. There are actually two reasons. One is trivial. The first reason is, of course, that we look for the maximum per se, right? The other reason, which is more profound, is that we have a disbalance here between the day and the night side, right? So there's, of course, more energy available on the day side than on the night side, and this disbalance, of course, the system tries to find an equilibrium, and well, this heat engine. So somehow intuitively you could say this heat engine probably tries to work in a way that that the equilibrium is approached as quick as possible, right? So this is kind of so this is a little bit it's very hand waving actually, right? So two reasons actually once again to look for the maximum here. One is that we are looking for the maximum efficiency, and the other is that there's a good reason to, at least intuitively, to believe that the system, that this heat engine called atmosphere works close to the maximum efficiency of converting solar radiation, of balancing the imbalances on the planet. Of course, what we now can do is to use this maximum. So what we can now do is to use this maximum, which is in all the cases that we look at. So if we try to draw a line here through the maximum, more or less straight, then you find that all these, so this was not very good. You find that all these maxima are, okay, this is this system that, so makes no sense. But you see these maxima are all around 0.3. And then we can use this and plug it into our formulas that we derived for T3 and T4, right? T3, and so we can calculate T3 and T4. So actually we just need to calculate one, and the other we get from the Carnot efficiency. So what we could do is to calculate the temperature. Calculate the temperatures. And now if we use equation, where is it? Equation for T3. So equation 15. So from equation 15, we get, we would get something like 325 kelvins. That's a lot, right? And then using the Carnot efficiency, namely we said 0.3 is equal to 1 minus T4 divided by T3. Then what did I do here? So what I get here is T3 is equal to 325 Kelvin. And from that, using 0.3 is equal to eta is equal to 1 minus T4 over T3. I would get T4, and this is 227 Kelvin. So this is very cold. And if you look into the paper by Gordon and Sami, then the discussion in that paper is actually a little bit questionable, because what they say is they take these two temperatures actually not as day and night side. They say this is kind of the surface temperature. They calculate a slightly different number, and they say this is the temperature of the upper atmosphere, right? So in something like 30 kilometers height. But actually there is no exchange, there is no wind between ground level, between the troposphere and the stratosphere. Right? So all the wind takes place in the troposphere up to a height of something like 10 kilometers. So therefore, this is a little bit questionable what they write in this paper. Okay, anyway, what we could do is, however, that we try to compare it with reality. So what we have here on Earth, right? So this would be the final points here, comparison with reality on Earth. So how much watt per square meter would we produce according to this model, and how much do we observe in reality? So we know that the mean solar radiation, so if we average the solar radiation over the entire surface of Earth, right? What we then get is the famous solar constant times, of course, the albedo, right? So what we get is pretty much close to 1 kilowatt of solar radiation is absorbed per projected area. And if we want to calculate the mean over the entire surface, then we would have to divide it by 4. Right? So what we get on average on Earth, averaged over all latitudes and over day and night and so forth, is 223 watts per square meter. Right? And now, according to the Gordon-Samy or the de Vos-Vlader model, we convert approximately, or at maximum 8% of that into wind energy. Right? According to Gordon-Samy or de Vos-Vlader, about 8% can be converted to kinetic energy. Meaning wind. And, well, 223 watts per square meter times 0.08, this is 18 watts per square meter. And in fact, so in reality, it's just 7 watts per square meter. We have 7 watts per square meter. Well, but considering this very rough model, it's actually quite interesting that we are on the right order of magnitude. One note on that. So you might say, oh, only 7 watts per square meter? And then if I take into account that we can't build a wind turbine on the oceans, in the Pacific, say, or on high mountains, and so on and so forth, right? How can it be that wind energy can be a significant energy source? I give this question to you, so think about it for a minute. So when you think that we can perhaps plant only wind turbines on, well, a percent of the land surface, so which then means a small fraction of the total Earth surface. So we can't plant any on the South Pole or North Pole, right? So why can wind energy be a substantial energy source? So in the first lecture I said that wind energy can provide the entire primary energy demand on Earth. How can this be? Right? So with this number here. Solar energy can provide 10,000 times the world energy demand, or 7,000 times, or something like that, at least on that order. And now I take fractions of that, right? Small fractions of that. So 8%, and from this 8%, perhaps a fraction of a percent. Any idea? No? Well, I mentioned this at some point, but I guess that this was not noticed by most of you. There's a huge difference between wind and solar energy. Right? So solar energy you can only harvest immediately. Right? But wind energy, so the wind that is generated on the oceans, at least a fraction of that wind, actually a large fraction of that wind, will eventually make it to the place where you have a wind turbine. Yeah? The same applies for water, for hydropower. Right? So the rain that falls in the Alps is collected by all these rivers, right? And then you put a power plant, a hydropower plant, somewhere, at a big river or something like that, right? Not as extreme for wind, but wind that is generated in a place where you can't plant a wind turbine. This wind nevertheless makes it around the globe, right? So that you can actually harvest it by a wind turbine. Okay, yeah. So a remark here. Yeah. Wind power is nevertheless a globally significant energy source, because wind generated for example, above the oceans, so the kinetic energy of that wind, so generated above the oceans, will eventually, or can eventually end up at places where wind turbines can be built, can be installed. Yep. Okay, and then 2 or 3 final remarks for discussion why we have this discrepancy between 18 watts per square meter and 7 watts per square meter. Well, so reasons for the discrepancy. And the first one would be, it is not clear that the Carnot engine called atmosphere, the Carnot engine, atmosphere, no, this is not what I mean. This is actually wrong. It is not clear that this is actually what I just wanted to avoid. It is not clear that the heat engine I should write, atmosphere, works at maximum solar efficiency. it's just an upper limit, what we calculate here, right? The next reason is, of course, that there may be other means of thermal exchange of heat, namely just by heat conduction, for example, or there may also be other modes by, say, by latent heat. Yeah, so if you create water vapor and then it condenses again, yeah, so this not necessarily creates wind. And we could model this as heat leakage between warm and cold. Yeah? So heat leakage between warm and cold. And so just that the Earth rotates and takes with it, of course, the atmosphere would also contribute to this heat leakage. And of course, the model of a hot day side and a cold night side is wrong for us. Good, this concludes here this subchapter on this Gordon-Samy model and on the de Vos-Vlader model. So I hope you had some, so you find this intriguing, these simple models. So I like this kind of modeling. Next time we would talk about global wind systems, how they are actually in reality. So you might know from school the Hadley cells that are responsible for the trade winds. So for my German students here, Passatwinde. So there are global wind systems that we want to discuss briefly next time. And then I give a brief glimpse on how one could modify this, the model that we have drawn up so far, to correspond a little bit closer to the wind systems that we have on Earth. But then we would assume a more local perspective, namely how the wind looks like, how the wind behaves on a more on a short distance scale, and this would bring us then pretty quickly also to wind turbines, I think, in beginning with the 8th lecture or so. With this, I thank you for your attention and have a nice week. Thank you. So.